Andreea Diaconescu, who is joining us from Toronto. She's a professor at the University of Toronto in the Department of Psychiatry, and also an independent scientist at the Krembil Center for Neuroinformatics. She's particularly interested in mathematical modeling of maladaptive behavior and whole brain disconnectivity in psychiatric populations. The presentation will be on modeling abnormal beliefs using Bayesian inference. We're very much looking forward to that.
Thank you so much for that great introduction, and thank you for the organizers for inviting me to give this tutorial today. So today I'm going to talk about modeling abnormal beliefs using Bayesian inference, and this is one of my favorite quotes that reflects some interesting beliefs that can emerge from changes in the statistical properties of the environment. So first, I would like to begin my presentation acknowledging my mentors, collaborators, and students at the Cognitive Network Modeling Group in Toronto at the Krembil Center for Neuroinformatics, and also those throughout Europe that have been longtime collaborators, friends, and mentors. I'd like to give a special thank you to Klaas and Stefan and to the Translation Neuromodeling Unit, because a lot of the concepts that I will discuss today, I've learned there. So one of the themes of this meeting is revisiting the question, what does the mind think of the brain? And today I will attempt to present a unifying framework for understanding cognition that is based on Bayesian inference. So in short, the Bayesian brain hypothesis proposes that the function of the brain is to cast predictions about true hidden states in the world and to update those predictions through sensory data by incorporating surprise signals that reflect the discrepancy between one's model of the world and the sensory inputs or the evidence experienced. First, some definitions. So beliefs, we assume that beliefs can be represented as probability distributions. And if they are Gaussian, they can be represented by their two moments. And those are the mean and the precision, which is the inverse of the variance. So we can say that the probability of X is normally distributed with a mean of mu and a variance of sigma squared. We can express exactly the same thing, but just in terms of precisions. So the probability of X is normally distributed around mean of mu and precision pi, which is the inverse of the variance. So what are the relevant variables of interest when we want to model aberrant beliefs? Those are states, parameters, and inputs. States are quantities that evolve in time and whose dynamics are of particular interest to us. So I use the notation x of I at time point k, where I is the level. Usually, I will talk about simpler models where we're not particularly interested in the particular level of inference, but I will also discuss hierarchical models where the level is important. And k is the time point. Now, parameters are the structural determinants of the states, and they determine the dynamics or the evolution of those states in time. And the parameters are, you can think of them as subject specific, and they reflect they provide a concise representation of those interesting dynamics that we might want to assess when modeling, for example, abnormal behavior. Now, the inputs are perturbations that occur at each time point. So we talk about inputs U at time point K. We're talking about variables that evolve over time for N trials. And often in this presentation, I will use state equations, which are difference equations. So x at k+1 is a function of x at time point k, theta, and u at time point k. Now, how do we represent these state space interactions? Well, we assume that these state space interactions evolve over time, and in addition, they depend on the previous state in a Markovian fashion. They generate the inputs at each time point u, at each time point k, and the inputs are u. And the measurement or the response equation provides a forward mapping from these hidden states onto the observed responses. So according to this proposal, we can hypothesize that cognition is an active process, such that an agent makes predictions about hidden states in their environment and maintains or adjusts these predictions through surprise signals or prediction errors, inputs that reflect the discrepancy between the world and one's predictive model of the world. So on the one hand, we have a generative model that describes how the true hidden states actually generate the inputs that we observed. And on the other, we have an inference process that refers to how an agent approximates these true hidden states based on the observed sensory input. Now, at the heart of this formalism is actually the Bayes rule. And according to the Bayes rule, beliefs are conceptualized as probability distributions, and they're updated via the Bayes rule, where predictions change as a function of the sensory input, the sensory data, and prior beliefs. That is normalized by at the evidence, the model evidence. Now, Thomas Bayes was a clergyman, but also an amateur scientist and mathematician. He studied logic and theology at the University of Edinburgh. And the Bayes theorem first appeared in his essay Towards Solving a Problem in the Doctrine of Chances, which was published 3 years after his death. Now, the Bayes theorem was used to convert a prior probability into a posterior probability by incorporating the evidence provided by the observed data. So the quantity P of data Y given theta on the right-hand side of the Bayes theorem is evaluated for the observed data set Y and can be viewed as a function of the parameter vector theta under the model M that is assumed here. And this is called the likelihood function. And the likelihood function expresses how probable the observed data set is for different settings of the parameter vector theta. So given this definition of the likelihood, we can state the Bayes theorem in words. The posterior is proportional to a prior and likelihood, where all these quantities are viewed as functions of theta. Now, the denominator is a normalization constant, which ensures that the posterior distribution on the left-hand side is a valid probability density and integrates to 1. Now, what do we have on the denominator? So the model evidence. The model evidence is the likelihood that the data were generated by model M, averaging over all parameter values as weighted by their prior. And it's an index of model goodness. And it is something that we can use to compare models to each other. Now let's consider a simple example, a binary one, such as a coin toss. And the probability theta is the probability of getting heads, of flipping and getting heads. Let's start without any data. So first, we can assume a uniform distribution, which means that our possibilities are equally likely. In other words, we have a beta distribution with parameters 1 and 1 that ranges between 0 and 1. However, common sense would tell us that the probability of receiving heads on a coin flip is 0.5. And we can express this mathematically by increasing the parameters of our beta distribution to concentrate the probability around 0.5. And now we can calculate the probability using an experiment and flipping a coin 10 times and recording the outcomes of each coin flip. Now we can quantify the results of our experiment using a likelihood function. And this is represented here by a binomial distribution. So now we can use the Bayes rule. And the Bayes rule allows us to update our beliefs about the parameter following this little experiment that we did by multiplying the prior distribution by the likelihood function. In this case, the beta distribution is a conjugate prior for the binomial distribution of the likelihood. And this ensures that both the prior and the posterior have the same distributions, in this case, beta distributions. Now, I'll show this little animation that tells us what happens when we have different types of priors. So let's say we start off with an uninformative prior. The likelihood function overlaps completely with the posterior distribution, which is plotted here in blue. But because it overlaps, it's masked by the posterior distribution. But now, using common sense or using a more precise prior distribution that reflects our subjective beliefs or past experiences. Sorry for that. Let's try that again. Yes. So if we use more informative priors, then those more informative priors, we have a greater influence on the posterior distribution. On the other hand, if we collect more data and if we have larger sample sizes, this will give the likelihood function a bigger influence on the prior distribution. But if we have informative priors, this means that we can obtain precise estimates of the posterior distribution even with smaller sample sizes. And this is something that is quite critical to keep in mind. Now, when we think about these uninformative priors, we might wonder, okay, so then how do sort of frequentist approaches compare to Bayesian approaches? Is it similar to, when I take a frequentist approach, is that similar to using an uninformative prior or a flat prior? Well, not exactly. In both Bayesian and frequentist approaches, the likelihood function, this probability of y given theta, plays a central role. However, the manner in which it is used is fundamentally different. So in a frequentist setting, theta is considered to be a fixed parameter whose value is determined by some form of estimator. So you have, let's say, theta hat. And error bars on this estimate are obtained by considering the distribution of possible data sets y. But by contrast, from the if you take a Bayesian perspective, there's only a single data set y, namely the one that is actually being observed. And the uncertainty in the parameters is expressed through that probability distribution over theta. Now let's consider different categories of prior. So we've talked about these non-informative or uniform priors. We can also employ subjective priors, which are not necessarily, which are subjective, but they're not arbitrary. They can be hypothesis driven or the result of previous empirical studies that we might have performed. So we incorporate that knowledge that we've accumulated into the specification of those priors. When we have models that have a large number of parameters, for example, highly nonlinear, we might want to use shrinkage priors, that have a very small variance or high precision, and they emphasize regularization and sparsity. We can also use empirical priors. Empirical priors essentially involve learning the parameters of prior distributions from the data. This is also called empirical Bayes. So today's posterior is tomorrow's prior, so to speak. And these are essentially the different influences that, for example, on the one side of the spectrum, shrinkage priors might have compared to non-informative priors. So essentially, they might determine, they can determine how much data we need to acquire in order to have a precise posterior estimate. Now, in the real world, we have a lot of questions or interesting problems that we want to solve that are non-binary, such as, and they're continuous and changing in time, such as, for example, temperature estimate. You want to figure out how warm it is outside to make a decision what to wear. Should I wear a jacket, a sun hat, shorts? Now, your prior information is very valuable here, because you could say that given the season, given the time of day, that will determine, that will predict how or determine a certain distribution around a particular temperature, such as, let's say, today in Toronto, 25 degrees in the morning, let's say, based on our knowledge of the season. Now, you can use the sensory data, you can measure the temperature outside kind of empirically, and this allows you to sort of compute a posterior distribution that will allow you to choose the best course of action of what to wear. Now, in the temperature estimation scenario, we have sort of a continuous measure, the tendency for the temperature to be high or low. And let's say this is what we want to infer on, to assess. And let's say that's why it's a combination of theta and measurement noise. And we can define a likelihood and a prior. In this case, let's assume that temperature is distributed in a Gaussian fashion. So we have the probability of y given theta is normally distributed around theta and sigma squared. And that's our likelihood function. Now the prior, the probability, we also assume that the prior is normally distributed, or is a Gaussian, probability of theta around is normally distributed with a mu and a sigma squared. Now, one nice thing about Gaussian distributions is that the conjugate prior is also a Gaussian. So we are only dealing with Gaussian distributions in this case. And the posterior is also a Gaussian with p of theta given y around a mu and sigma squared. Now, how do we sort of combine the likelihood and the prior to obtain the posterior in this particular way? So essentially, we have two sources of noisy information. Our prior beliefs are noisy. They are based on previous experiences, noisy experiences, or imperfect knowledge. And then we also have the measurement noise added on top of that. So how do we optimally integrate these two sources of noisy information? So here we can compute a posterior precision and the posterior mean by integrating these two sources. So the posterior variance is the sum of the likelihood variance and the prior variance, and the posterior mean is the variance weighted combination of the prior mean and the data to obtain the posterior. Now we can express the same thing in terms of precisions. So now we have the posterior precision, which is the precision of the data plus the precision of the prior. And then we have the posterior mean, which is now a precision weighted combination of the prior mean and the data. So we weight the data and the prior mean by this precision ratio, the precision of the data over the posterior precision plus the precision of the prior over the posterior precision. And this is one example of a precision ratio weighting, which will come up again and again during this presentation. Now, it's important to note that we are dealing now with two different perspectives. So we have Bayes versus Bayes. What does that mean? So the Bayes rule is a statistical rule that describes the relationship between conditional probability distributions, but we can think of it from two different perspectives. We can think of it from the perspective of the environment, the world, and applying theta to understand a phenomena or a process, and apply the Bayes rule for model fitting and parameter estimates, and obtaining the model evidence in order to perform model comparison. But on the other hand, when we're thinking about abnormal beliefs, let's say in the context of psychiatry, the Bayes rule becomes a model of a computation that might be performed by the brain. And in this case, the Bayes is a model of behavior, or can be used as a model of behavior. Let's go back to this again. So, let's take the tenet that the Bayes rule is a model of computation performed by the brain. So we can think of perception as Bayesian inference. We can think of cognition as Bayesian inference. So we have this dichotomy between the brain and the world. So on the one hand side, we have the generative model that the the underlying latent causes for the sensory data that the agent observes. And on the other hand, we have the inference process, how the agent tries to approximate the causes, those true hidden states. So based on an internal, and as experimentalists, we are particularly interested in the left-hand side here, in how the agent infers or approximates these true hidden states. So let's assume that the agent has an internal model of the world. And essentially, this is the prior, it's the probability of the state of the world. And based on that prior, an agent is going to make predictions about those hidden states. And they will maintain or adjust those predictions through the sensory data. That's our likelihood. Now, the updated model is the posterior that reflects the degree to which an agent updated their beliefs in light of the likelihood and incoming sensory data. So what is optimal integration in this case? Optimal integration is precision weighting, or integration that takes into account uncertainty. So here, we go back to this temperature example. Let's say now we are taking a slightly different perspective, and the perspective of observing the observer. Let's say we try to infer how another agent is estimating temperature in order to decide how to dress. Now, we have a generative model of beliefs that could be described also using Gaussian distributions. And now we can optimally integrate these, the likelihood and the prior using this precision weighting ratio, just as in the previous example. Now, there's a lot of interest in modeling aberrant beliefs and sort of suboptimal learning and how that might be described. But first, let's ask the question, what is optimal Bayesian learning? And optimal Bayesian learning, also synonymous to using a normative model of the world, is a model basically where we have a minimal divergence between the inferred state and the true hidden state. But when we think about in the context of psychiatry and trying to understand variability in behavior, we are actually interested in this sub-optimality. So how essentially trying to quantify this reduction or this increase in the divergence between the inferred hidden states and the true hidden states. And one might ask, okay, how do we model abnormal beliefs? There's different ways. So on the side of the prior, we could have the wrong priors where uncertainty is too low, meaning the beliefs are too rigid. Uncertainty is too high, which means that an agent is highly sensitive to noise and overfitting. Or there's a displaced center of mass. The beliefs are biased. We could have an overestimation of volatility where prior knowledge is partially neglected, an underestimation of volatility where an agent fails to track important changes in the world. Or we can look at the likelihood function. Perhaps the likelihood function is suboptimal, meaning that precision is too high or too low, or sensory evidence is weighted too much or too little. So we could hypothesize these different ways in which beliefs could be suboptimal, either overconfident, underconfident with a reduced precision, or biased. Now, how are these beliefs formed? Well, before we make the next observation, let's say in terms of the temperature estimation example, our belief about the true value of the state can be described by a Gaussian prior. Now, the likelihood of an observation U is also Gaussian, and it has a precision pi. Now, the Bayes rule tells us again that our posterior is Gaussian. So we try to update to, we update to the sufficient statistics. So here we use exactly the same functional form as before. So here we have the mean, the update, the update, the mean, and the precision. The mean is updated by an uncertainty weighted or precision weighted prediction error. The size of the update is proportional to the likelihood precision and inversely proportional to the posterior precision. Okay, so we have here, this is the belief update, the degree to which we change our beliefs given new sensory input. And this is proportional to a precision ratio multiplied by a prediction error. Prediction error is the discrepancy between the input and our prediction, and the precision ratio is this likelihood precision over the posterior precision. And this is analogous to a learning rate. So in reinforcement learning model, this would be akin to an alpha, a learning rate, which is in this case, in the case of reinforcement learning, it's a constant parameter. In this case, this is a state that evolves in time and reflects how much we're learning here and divided by how much we already know, how much we already know about the state of the world. Now, what about dynamics? Because obviously temperature is a non-stationary process and it changes over time throughout the day or throughout the seasons. So we want to relax the assumption of stationarity and assume non-stationarity. And this way we can replace the hidden state X, we can replace it with a Gaussian random walk. And what that gives us, and very simply speaking, is the Kalman filter. And the Kalman filter provides us with an adaptive learning rate that accurately reflects the changing nature of the environment. So in the Kalman filter, we have the generative model here. So we have Gaussian distributions. Now this is the tendency of the temperature to be high. And now with in here with the Kalman filter, we have a parameter that determines the dynamics of that tendency, such as theta. And in this case, we can think of theta as the changing seasons or the changing times of day that determine the variance of that state or the dynamics of that state. So with the prior described in this Gaussian form, the belief update is a precision-weighted prediction error again. And the same equation that we had before is shown here. So we have here the belief update, how much beliefs are changed in light of sensory input, in light of the prediction error that are weighted by this precision, the precision of the input or the precision of the sensory data that is divided by the belief precision. Now, the Kalman filter is an optimal model for linear dynamical systems. However, for linear dynamic systems, however, except for very simple physical systems, the world is not linear. And living organisms need to adapt and filter those inputs in light of changes over time. In other words, we have to acknowledge that a lot of processes in the world are volatile, they are changing, and we can assume that agents will infer on that changing structure of the environmental context, and that will determine how we're learning about the tendency, in this case, temperature. So the temperature fluctuations, for example, could change over time as a function of another quantity that captures rate of change or volatility, such as, for instance, climate change. So that so changes in climate, for example, will lead to have an impact on our predictions of temperature, and they can have an impact in a very specific way by modulating, by affecting the precision or the variance of our beliefs. So we are increasingly more uncertain about events in the world. And one such solution for nonlinear systems is the hierarchical Gaussian filter proposed by Christoph Mattis and colleagues. And the hierarchical Gaussian filter provides a generic solution to the problem of adapting one's learning rate in a volatile environment, and proposes that states evolve in time as coupled Gaussian random walks. And the generative model assumes hierarchical causes of those sensory inputs. So the inputs experienced by the agent are the output of associations whose strength changes in time. And this is the mathematical formalism for the state. So one thing to add here is that the variance of the tendency, in this case, temperature, for our example, the variance is determined by the next higher level, by the volatility. So an increase in volatility will ultimately lead to an increase in the variance of that tendency or of the temperature. And the degree to which volatility impacts the variance of the level below is determined by a set of parameters, kappa and omega, parameters that determine the, such as kappa, that determine the degree of coupling between the hierarchical states. And it's important to notice that the hierarchical Gaussian filter is a filter that can increase. So we don't have to stop at the third level. We can have a volatility that impacts the variance of the meta volatility and so on. But if we reduce the HGF to one level, then it is equivalent to the Kalman filter, which I mentioned before. Now, let's go back to the perspective of the agent in the world. So we talked about this generative process and the inference process. And here we have an advantage. As the experimenter, we have a handle, or we have knowledge about the generative model, the generative process that is causing the sensory input. That is essentially our cognitive task. that we propose in our experiment. But we are actually interested on how the agent infers on the causes of that sensory input. So we can think of it as a dichotomy. You have the HGF proper and the HGF as a generative model. So on the one hand, we have HGF as a model of inputs that change in time as a function of the association, the tendency towards a certain category, which in itself changes as a function of the phasic volatility. But on the other hand, we have the HGF as a model of beliefs, beliefs about tendency, beliefs about volatility that are Gaussian in nature. Now, how are these related? So the inversion of the HGF to generative model proceeds by introducing a mean field approximation and fitting quadratic approximations to the resulting variational energies. And this leads to simple one-step update equations, which is the HGF proper for the sufficient statistics, the mean and the precision. And we have this expression, so updates are precision-weighted prediction errors, and the degree to which one adjusts their model of the world is not only dependent on the prediction error, but also on a ratio of precision. In the numerator, we have the sensory precision, which amplifies the impact that prediction errors have on the belief updating process, whereas on the denominator, we have the belief precision or the agent's top-down confidence that their model is correct, that leads to a dampening of the impact of incoming prediction errors. And this is equivalent to reinforcement learning. Now we can unpack this precision ratio even more for those who are interested. So we have the outcome precision, and we have two additional sources of uncertainty that are particularly interesting. That one has to do with informational uncertainty about the probabilistic association that the agent is learning, and the other about the environmental uncertainty. And I want to conclude essentially by showing an example. This is a simulation. So here we want to relate Riscola-Wagner learning that uses a learning rate or a constant weight on the prediction error to the hierarchical Gaussian filter. So essentially that alpha is now a precision ratio that reflects the impact of those two precisions. So let's say we simulate here temperature changes with a gray line. So this is the input, the probabilistic input that the agent observes about how temperature is changing over time. And in the colored lines, we have the different learning rates. In blue, we have the lower level learning rates, and in red, the higher level learning rate. And if you zoom into the learning rates, what is interesting is that if you compare the alpha to the first level learning rate, what you see here is that the hierarchical Gaussian filter learning rate is fluctuating around the alpha, but now it's lower when the environment becomes more stable, and it's heightened when the environment becomes more volatile. So this is essentially the learning rate in this case is incorporating context in order to update beliefs, whereas the Riscola-Wagner learning rate is too high when the environment is stable and too low when the environment is volatile. And we have different ways of applying these types of models to model abnormal beliefs, which I will leave for the discussion. But essentially, one example that I'd like to leave you with is how we might model psychosis and the different phases of psychosis by taking into account this precision ratio that impacts has an impact on incoming precision, on incoming prediction errors. And with that, I would like to again, acknowledge. Can't seem to go to my next slide. Sorry for that. just before before I end, my apologies. I want to highlight sort of how we might think about abnormal beliefs when we take into account this this precision ratio, the sensory precision compared to the belief precision, as marking the different phases of psychosis and dissociated between the delusional mood and the delusional conviction. And with that, I'd like to thank again my mentors, collaborators, and students, and thank you for your attention.
Thank you very much on behalf of everybody listening for this really great educational talk, which I think was a model talk in its beautiful illustrations and also the clear examples that you gave. So thank you very much.
Thank you.
Also for staying on time perfectly. So we have time for some questions now. And
shall I read out?
Oh, yes,
you will
maybe
read the
if you're reading along, I mean, you can take them directly. If you take
okay,
them from
perfect. So I will start with Morris Friedman. For delusions, is the prior in your model operating with a block in the effect of the posterior, i.e. there is no belief update? So this is a good question. In the case of delusion, actually, there's a lot of evidence that the prior beliefs have a strong impact on the belief update. And the way they can do that is not by blocking learning, so to speak, but if you remember this belief precision in the denominator, when that belief precision is really high, then the weighting of incoming prediction errors is low. So even if exposed to disconfirming evidence, then that evidence is discounted because, in other words, because the agent believes that they already know the state of the world and those incoming prediction errors might just reflect random noise. Theodora Stoica, thank you very much for the talk.
Excuse me, if you maybe if you go to the answers tab, because some of the questions were voted up, so they're sort of pre-digested already.
Okay.
Yeah. So if you click over to answered and then
answered, okay, perfect. So I will say anonymous attendee, I believe, is the first one. So thank you for an interesting talk. Can you give an example how to apply the concept of attractors when we are looking into higher order? Oh, no, this is Victor's answer.
And I think Victor has taken care of that.
Okay, perfect.
The next one would be a little bit further below by Thomas Barley.
Okay. But I just wanted to say that even in this type of mathematical formalism, the concept of attractors is actually important and might reflect sort of drifts drift states that beliefs approach over time. So just wanted to make that point, like Ornstein-Uhlenbeck process, for example. Thomas Farley, thank you for your talk. One question is the Bayesian framework that you're proposing here, a model that external observer, us scientists, could use to model learning in agents. Yes, that's correct. So the Bayesian framework proposing here can be used to model learning and model behavior. Or are you suggesting that the brain itself is implementing a Bayesian inference engine with populations of neurons representing priors, or a connectivity structure optimal for Bayesian inference? Yes, this makes a lot of sense. And in my talk, I didn't touch on the implementation level. So how Bayesian inference might be implemented in the brain. I believe that this will be the topic of other talks at this conference, but essentially there is still evidence that neuronal populations represent priors and that certain changes in connectivity could reflect belief updating. Okay, what sort of evolutionary purposes might have driven the brain to evolve and develop a Bayesian engine? Well, the evolutionary process, first of all, is that we want to minimize surprise and accurately predict states in the world. And there's, survival, objective function there. We want to optimize our survival, and to do so, we need to accurately predict true hidden states in the world and avoid predators or avoid death, right? So in this formalism, this hierarchical formalism is quite compatible with evolutionary theory by assuming this hierarchical structure and volatility having an impact on the evolution of states, and the assumption that agents infer on that volatility, because the environment is stochastic, is constantly changing, requiring the agent to adapt to it. However, the degree of adaptation is important because we don't want to adapt to any noisy fluctuations. We want to adapt to whatever improves our survival.
Then we also have a question from the audience. Somebody who raised their hand.
Yeah.
Ken, I just unmuted you if you want to go ahead and ask your question. You'll have to unmute yourself now.
See that Ken raised his hand, so maybe if you speak up and unmute. Not sure, it may not be working.
Perhaps. Maybe go ahead and take another question from the Q&A thing then for the time being.
Then maybe we take the next question as we still have 2-3 minutes from the Q&A. So one question: are errors in interpretation of empirical data, like someone who suffers from a persecution delusions despite evidence to the contrary, represented differently in the Bayesian equation? That is, do you add an error variable to the equation that has some weight on the Bayesian equation that represents an agent wrongfully interpreting sensory information? I think you partly answered that, but it may be good to reiterate.
Yeah, so there's no need to add any variables. Actually, this belief update proportional to a precision-weighted prediction error gives you basically the answer. So in the cases of persecutory delusions, then it's actually the posterior precision, the belief precision on the denominator will dampen the impact that contrary evidence will have, or incoming prediction errors will have. So that belief precision, that heightened belief precision, will shape the way an agent views the world.
Then we have a question from Theodora Stoika. Thank you very much for the talk, Andreea. And then I can't pronounce it properly, I'm sorry.
Yeah.
You described the relationship between an agent and the world, but have researchers investigated how two agents and their predictions, updates, etc., may interact with one another? For example, if two agents disagree on their subjective beliefs on the temperature in the house car, and how that may impact their updating.
Yeah, definitely. So this is actually a very important topic. This two-person interaction modeling is quite critical when thinking about how cohesion of beliefs has an impact on the belief updating process, how persecutory delusions or paranoid beliefs might form. And there's been research in that area, and I would like to point you to the work of Jean Donizeau, with interesting applications in autism as well, in theory of mind. In a lot of the cases that we're looking at, and some of the examples I presented here, you have the generative model right on the right-hand side. So that's the experimental structure of the task. In the two-person modeling, that would be another agent with their own model of the world, their own precisions and beliefs. In that case, it's a bit more complex because it is harder to compare parameters across subjects, because essentially they are experiencing a different environment. They're experiencing a different interaction, a different agent. So for many applications, the generative model is kept constant and fully controlled by the experimenter to allow these comparisons between agents.
We do have some more questions showing the interest in your presentation, but in the order of timekeeping, I would suggest that maybe you keep answering them in the Q&A. And there's also a suggestion for anybody who still has a question now, please enter them. The panelists will see your questions and may respond to them in the written format. First of all, let us thank you again for this wonderful presentation. And
thank you so much.